Yeah, once we know how to evaluate the vibration characteristics of automotive structure or any structure, next comes the important topic, that is optimization or diagnostic techniques. We need to somehow eradicate or at least reduce the effect of these vibrations. As I already mentioned, we have to calculate the modal frequency response functions or FRFs to get information about the modal characteristics. Then we have to calculate the modal participation factors. Modal participation factors, it gives information about how a particular mode is being influenced by the modes at different frequencies. For example, suppose I have a roof mode of a bus at 10 hertz. This mode is actually being affected by the modes at different frequencies in the neighboring frequencies. For example, at 8 hertz, 9 hertz, or 11 hertz, 12 hertz. All these frequencies, all these modes also will contribute to this mode at 10 hertz. So we should know how much is the contribution from different modes at a particular to a mode at particular frequency. This is done by using modal participation factors, and this will be further used for the fatigue strength evaluations. Then we have the panel participation factors. Panel participation factors are mainly for vibroacoustics. For example, as a driver or passenger, you are sitting in the vehicle, and because of certain panel, because of certain body in white panel, you are able to hear a lot of noise. Using these panel participation factors, we can identify which panel is contributing how much to a noise at a particular response location in your vehicle. This is panel participation factors. Once you know this, we can modify this particular panel, say by adding some stiffeners, or by changing the thickness of the panel, or doing some kind of diagnostics. We can eradicate this noise. Then comes the energy distribution analysis. Energy distribution analysis is mainly used to identify whether your modes in the system are coupled or decoupled. Coupled modes are always unwanted, and you should avoid these coupled modes. For example, say at 10 hertz we have a certain mode of vibration, and we will calculate the energy distribution, say the kinetic energy or potential energy, say strain energy at this particular frequency. If we have the energy distributed at a particular mode for only at that particular frequency, there is only one mode, then it's fine. But at a particular frequency, if we have more than two modes, for example, we have bending as well as the sidewise movement of your walls or some structures, it's always coupled. In that case, it is not good, and we should somehow try to decouple these modes. So in this way, the energy distribution analysis helps you to identify the nature of modes in your system, whether it's coupled or decoupled modes. Then last but not the least is model assurance criterion analysis, also called as MAC analysis. It's mainly used for comparison of the results. Maybe it is a comparison between the test and the test results, or test and the simulation results, or simulation and simulation results. Just to include one information, simulations or numerical models are always just a kind of assistance to the testing procedures. It's always through the test your model or your structure or your any component that you design will be approved. So simulations are just assistance. So it's always important that your simulation results are in accordance to the test results. So in this way, MAC analysis help you out to compare this test and simulation results as well. Then coming to the current trends in the industry, of course, lot of digitalization is happening in industry, and it also applicable to the testing. For example, lot of development of virtual test rigs to predict the vibration behavior of different components at the subsystem level as well as the full vehicle level is performed. For example, my thesis topic, I was working on developing a virtual hydropulse test rig to predict the vibration behavior of the interiors of the bus. Why we do this is basically we want to avoid the repetition of the costly prototype test. We want to use a simulation model which is very close to the testing model or the test scenario, and we would like to evaluate or predict the behavior of the interiors or behavior of the any structures in terms of vibrations upfront. In this way, in case of a failure of these parts, we can redesign these parts virtually, and we can go ahead with the development. So in this way, what happens is that Once you reach the physical prototype testing, we have parts with high maturity levels and they are very unlikely to fail. This way we can reduce the number of prototype tests. Basically, it's all about the cost and time optimization of the product development cycle. And we also use the so-called digital streets instead of running a prototype vehicle which is very costly on the real roads. We have the virtual or CAD models or multi-body simulation models, and we run on the so-called digital streets, which represents very closely to the actual roads. In this way we can get also the interface loads, which is useful for doing FE simulations at different subsystem levels. Then of course comes the electric vehicle NVH. Yeah, as I already mentioned, a lot of research is going on in this aspect. The main difference between the electric vehicles and IC engines is that we don't have engine masking. Engine masking in a sense, previously in the conventional vehicles, we had the IC engines, which are the main sources of vibrations or noise in the vehicle. And so as you can see, it's 50% of the powertrain noise. And this IC engine was able to mask the noise coming from auxiliary systems like HVAC system or even the wind noise. It's only 10% in this case, and the loud noise is 30%. Once this engine is removed and electric motor is placed, this engine masking is not there in electric vehicles. So the wind noise, it has raised from 10% to 30%, and also the road noise has raised from 30 to 40%. So it's very important to consider the road noise as well as the wind noise in electric vehicles. And important thing to notice is that powertrain noise reduced from 50% to 15%. However, it's very important to consider this in electric vehicles because the electric motors, whatever the noise that they generate is because of the high tonalities, even the amplitudes are very less. Because of the tonalities, it's very irritating the passengers or the drivers. So a lot of research is going on in electric motor NVH. Then coming to the leading software providers, we have the software providers like Altair, Beta CAE Systems, MSG Nastron, Siemens for setting up the models, and we have the solvers like OptiSelect, Nastron, Abacus, and Parmas to solve the problems. Parmas is a German software provider, and OptiSelect is from Altair. Nastron is from MSE, and Abacus is from Dassault Systems. Important thing to notice is that we have so-called dedicated NVH directory in Altair, where we can do the entire simulation pipeline. We can execute the entire simulation pipeline using one single software, starting with meshing or preparing your model for simulation, then assembly, then you set up the load case using NVH director. For example, whatever the load cases that I have defined, that I have previously mentioned, say it is a unit load or it is a frequency dependent load or transient load, whatever it is, you define in this, and then you solve the problem. Once you get the solution, then you start post processing the solution. For example, what is causing problem in my system, how it is to be addressed, which kind of diagnostics method should I use. So it's all done during the post processing. Then we also can do optimization. For example, we can define optimization problem with a certain goal and some constraints defined over it. For example, say the maximum amplitude of vibration or maximum response that I can have is only 5 mm, and with a constraint of 2 mm thickness for the structure. In this way, you can get an optimized solution which satisfies the goal as well as obeying the constraints. And similarly, ANSA, it's also one of the leading software provider for finite problems. Here also we have a streamlined NVH pre-processing tool similar to Altair. Apart from that, we have MATLAB and Python. Yeah, these are primarily used for doing signal processing. Signal processing is something very important for an NVH engineer to know. For example, the transient signal or time domain signals that we get from the test, we cannot use them as such. We have to do certain kind of signal processing tasks. For example, generating an FFT frequency, it's a fast Fourier transform to transform from the time domain signal to frequency domain, and also for generating the frequency response functions or the transfer functions which I have mentioned, we can use some toolkits available in MATLAB and Python. it's good to gain some skills on this MATLAB as well, MATLAB and Python scripting. Then coming to the leading hardware providers, we have companies like AVL, Head Acoustics, Siemens, and Mueller BBM providing the hardware for especially for the measurement techniques. And head acoustics is very widely used across Europe, at least as far as my knowledge is concerned. And yeah, they provide all these sensors as well as the data acquisition systems, which is used for to collect the data at the different parts of the vehicle during the actual testing experiments. Then let's talk about the roles played by an NVH engineer at different hierarchical levels. At an entry level, say you are a graduate of a bachelor's or master's course, you'll start working on a subsystem level. For example, say suspension system or say interiors. You try to understand what's the physics behind the problem, and you try to optimize or diagnose the problems, optimize the vibration characteristics. Then once you become a CAE analyst, maybe after a few years of experience, you start working on full vehicle NVH analysis, where you will consider the effect of different subsystems, say how the effect of electric motor noise, how it's affecting the passengers or the driver, how steering and suspension system should be optimized with respect to the vehicle structure behavior. So in this way, start working on full vehicle NVH tasks, and you'll start you have to coordinate with the design and test teams, because the design, simulation, and test teams always have to work one in hand, because it's something very important to develop products in a quick and effective manner. We as simulations engineers, will be always communicating to the design engineers as well as the testing teams, and we support both the designers and the testing departments. Then coming to the top level, NVH lead engineer, yeah, you start setting up benchmarks. For example, for any new development project, for example, any new model of a certain company, they will ask you to set the benchmarks for NVH. How much should be the limit for responses in terms of accelerations or the forces? That's one of the important tasks. Then you start working also on the multi-domain optimization. For example, it's important for an engineer to also consider the different domains apart from the domain that you are working. You have to consider how the vibrations are going to affect your durability aspect, the safety aspect. You should start working together with the other departments. So in this way, you start working on multi-domain optimization. Then finally, we'll see how to get into this domain of NVH. As per my knowledge, one should have very good understanding of the structural dynamics, because NVH is all about knowing the dynamic characteristic of the structure, and yeah, it's very important to gain some hands-on experience in structural dynamics. And domain-specific knowledge is very important. For example, understanding what are the sources and how these affect the structures, say automotive or aerospace or ship industry, whatever the industry it is, you should know what are the sources and effects of these vibrations in this domain. Then good understanding of the NVH optimization and mitigation techniques, irrespective of the field in which you are working. You need to know how to diagnose the problems and optimize the vibration characteristics. Then understanding the relation, of course, between the NVH and other domains like durability and safety is important. When you are using finite element simulations to evaluate and optimize the vibrations, of course, you need to have a very good understanding of the finite element methods and basic understanding of signal processing techniques like the Fourier transformations and transfer functions or frequency response function estimation is very much needed as a development engineer in NVH. To summarize, first, we should try to figure out our domain of interest, whether it's automotive, aerospace. Then you have to start gaining hands-on experience in one of the leading FE model setup interfaces. For example, like Altair HyperWorks or ANSA, where we start building up the FE models, then starting to build assemblies, then perform simulations, then doing post-processing. All this will be done in FE model setup interfaces. Then it's important to understand at least one of the solver decks, for example, OptiSlug, Nastron, Abacus, or Permas, how the simulation is performed, what's the background, how the problems are being solved. It's very important to understand these solver decks. It helps you in debugging the simulation errors and any physics related problems. Then start working on real time projects and start understanding the physics behind the problem. It's very important. Work on optimizing the NVH related issues, and yeah, we can also, it's most importantly, it's like you have to follow the leading software providers, what's new with them, what's something new that they have introduced in the latest versions, and maybe follow the webinars. Yeah.